Okay, so first of all, I have some announcement to make. Let's talk about it quickly. Okay. And most importantly, what should you guys do for the reading week? As I mentioned before, to get yourself started for assignment number 2, and also for your project, and also programming test. Study this tutorial. I'll show you where it is, and then I'm going to write it in the announcement as well. But let me just show it to you so you can start right away if you wish after today's class. All right? So you got the reading week to actually finish that. So if you go to the lecture site for the course, you will see under tutorials, the first one, using the Antler4 parser generator to develop a compiler. Right? So to be assigned during the reading week. Well, this says pretty much, right? So the notes is over here. If you click on that, it's basically just like a YouTube video series over there. All right? I forgot the exact length. I think it's between 4 and 5 hours in total. So do plan your time throughout the reading week. I think it's going to be worth your time for sure. And I'm pretty sure you guys will study that. Take it seriously. Let me just give you a little bit items in perspective. Okay. So let me just tell you on the course calendar over here. Okay. Let me just put it here. Okay, we're now here. Lecture number 9, we're here. And reading week, please study the tutorial. And then in this week, when I say assignment number 3, don't worry. The assignment schedule is slightly delayed, but I'll make sure you still got enough time to actually study the updated calendar shortly after the reading week. But basically, it will be released, assignment number 2, in the beginning of after the reading week. And then I'll talk about quiz number 2 in just one moment. And don't forget, we already confirmed, your programming test is going to be on a Saturday on October 29th, 2 p.m. Right? We already said that. Okay, so please make sure you can make it to the programming test. And I will make sure you're properly prepared by the following. Number 1, you're going to study the tutorial. Number 2, I will also release a practice test. And this time, I can tell you for sure, the practice test I'm going to release is going to be more difficult than the actual test. Meaning that if you can complete a practice test with a relative confidence, you should be able to do well in the actual test. Okay? So it's a 4th year. The main intention for the programming test is not to kill your grade. It's really to make sure you know Antler4. All right? So I'll make sure I release that in the beginning after the reading week. Okay? So for your job for now, plan your time to study Antler4. And I'm going to host an office hour, mostly over Zoom, over the reading week, in case you got any question you want to discuss. I will also ask the TA to host an office hour over Zoom as well. The TA recently also went over the tutorial series. So if you got any issues to set up things on your computer, you can also talk to the TA. I'll give you all the details soon by e-class announcement. All right, so that's about the tutorial you want to study. You will see regular expression. You will see context-free grammar, which we'll get in touch. We'll touch that a little bit today. We'll definitely continue after the reading week. And for those of you who haven't really seen the so-called composite, basically tree, and visitor pattern before, don't panic. Just go over the tutorial video, note down your confusion or any point you want clarification, note them down. And after the reading week, I'm going to also talk about these 2 design patterns specifically. So I'll make sure you all understand what you're doing. Right? Just make sure you go over the tutorial first. Assignment number 1, due tomorrow, right? 2 p.m. If you haven't completed that yet, just submit your best effort. That's okay. But we're still going to give you feedback. All right? That's just don't miss the deadline. Okay. And for your programming test, as I said before, 2 to 3:20 on Saturday, October 29th. And the venue most likely will be in the LaSalle building. I'll confirm that a little bit later. Okay. Quiz number 1, I'll make sure I return it to you on the Tuesday after the reading week. I'll bring them back and then distribute the paper back to you. Also, I'll post some model solution to the quiz number 1. Accordingly, will you guys be okay, let's say, quiz number 2 is supposed to be on the Tuesday of our return. Would it be okay if you postpone that to the Thursday? Any objection? Okay. I want to make sure you guys are okay, right? If I make it earlier, then you might complain, but I'll make it later. Okay, just slightly. I can tell you my intention. If I'm only going to give you back your quiz number 1 graded paper, so you may want to take some time to think about it, right? So, but it's not directly relevant to quiz number 2, but I would say just give you some time. Okay, so I will confirm that also in writing. And let me see what else. Okay, what about the coverage for quiz number 2? Right? That one should be quite obvious. It's going to be from lecture 6 to lecture 9, what we're going to finish today. Whatever we're going to cover in lecture 10, it's not going to be covered. There'll be too few days for you to study. All right, I'll confirm everything in writing, but at least you have the idea. After the class, and before I post the announcement and video recording, you can definitely start with the tutorial. It's already up there on the YouTube. All right, guys, any questions? Let's move on to business. Minimizing DFA, okay? Right, that's kind of the motivation we talked about last time. So we just want to get a minimum number of states for the DFA in case the memory is sensitive in your computer system, in your case. And this is the algorithm, which I'm going to explain right now. What we explained last time was about the input and output. If you remember the little sketch we did, right? We did some sanity checks as well, just remember. And what I will do is, I'm going to go over the algorithm just line by line very quickly, and then I'm going to do 2 examples today, just to show you, given the DFA, how can you actually minimize its number of states. We'll see that. And then I'll leave one to you as exercise, and I'll post a solution maybe during the reading week. Right? So you got 3 examples in total. That should be enough. Okay, let's now take a look at this algorithm over here. All right. We got input and we got output over here. Okay, and it's going to be line by line. Okay, the first one. So we got 2 sets over here. We got P, and also we got T. All right. Initially, P is simply just empty. And the T here is basically a set containing 2 partitions. All right. Remember we talked about partition last time. You can think about each partition is just a set of states. All right. So initially we got just 2 partitions. You can think about this as partition number 1. Partition number 1, which will be all the accepting states. And the second partition over here is all the non-accepting states. You can see it's the set difference between the Q and the F. All right, partition number 2. Non-accepting states. This is how we're going to start with. Thinking this way, given any arbitrary DFA, we partition them into two sides. One will be accepting, the other one is non-accepting. This could be the minimum number of states already, partition 1 and partition 2, if we are lucky, that we substantially reduce the number of states. Or it could be that there might be more states than these 2 partitions, which we'll see in the algorithm. That's the overall idea. But let's take a look. All right, and here we say while P is not equal to T. All right, that's something I will try to do a little bit more explanation as we go over the example. You can think about when we say P equals T, this means it's not time to actually exit from the while loop. P equals T means no more optimization can be done. Optimization can be done, and it's now time to actually exit from the loop. And for those of you who are really into math, have you guys heard about an idea called fixed point? Kind of, don't worry. I'll put it here just in case. You can mention in the textbook, okay? But don't worry about it. I'm not gonna put it on the test or exam. I just want it for your knowledge. It's called fixed point. For those of you who are interested, you can look it up, fixed point. Whenever we reach a fixed point, we can exit from the loop. Basically, no more optimization to be done. Okay. Now, I want you to take a look at very quickly about how we change the P and T. You can see P is here, right? And P is here again. And T is over here. And T is over here. And then you can see T in the beginning of every iteration is simply set back to the default, just empty set. And then we're going to do some assignments on T, either over here or over here. And then notice that P initially is set to T. Right? So let's now try to understand the pattern over here. This is what we're doing. We don't really update the P. P is just going to keep the last value of T. And then we're going to go ahead, try to see if there's any way we can try to further optimize the DFA so far. If somehow the resulting T we got turns out to be just equal to T, in the, P, sorry. In that case, that means no more optimization is to be done. Okay, that's kind of symbolic suggestion. But we're going to see exactly how to do it. And then we're going to see in every partition there, we're going to find a maximal subset such that it's splittable. Right, let's go over definition, and then we'll do example. What does it really mean to be splittable? Splittable simply means somehow you can find some proper subset from the partition so that every state in the partition somehow can be led to the same partition, but that partition is not equal to P. Okay? That's okay, it's confusing, but I'm going to talk about example, right? And then we're going to do different conditional assignment here. Okay? I'm not going to ask you if you got any question. That's okay. Let's not go over example. But just remember, for every iteration, what we're going to do is we want to see if we can split from the existing partition any further. If we can, that means there will be another next iteration. If we cannot, that means we are done. All right? That's kind of the idea. Let's now see one example right away. That's the DFA. We want to optimize. That's the input. All right? Can you at least see what the DFA is trying to recognize? It's somehow trying to recognize some pattern of string, right? How many possible strings can we accept? 2. Either FEE or FIE. Agree? At least you can see that, right? Okay. Either FEE or FIE. I can tell you that ultimately we'll show this DFA here, recognizing FEE or FIE, it can be optimized, meaning that we can reduce the number of states. That's what we're going to do. All right? And I'm going to show you the corresponding line back to the algorithm. Number one, initially, we're going to have these 2 partitions. Accepting states, non-accepting states. That's the initial partition. So I'm going to use the coloring to show that. Accepting states will be here. They are in the same partition. Non-accepting states will be here. Are you okay so far? Yes, question.
I was wondering, each state does not have a transition.
Yes, that's a very good point. Yes, I forgot to mention. That's very good. By the way, this diagram here also came from the textbook. And the author actually explained over there, to really keep the diagram simple, there is some implicit so-called error states. I'm glad you asked. Because just by judging this, it doesn't look like a DFA, right? We can have some missing transition. Very good. Let me mention that right away. I was just about to say that. There is an implicit state over here, so-called either the error states or the dead state. Okay? Let me just say for SE, E for error. You can think about there are certain implicit transitions which we didn't draw. For example, you can see, let's say the alphabet here. The alphabet is simply from A, B, all the way to Z, let's say. That's the alphabet. Now, in this case, for S0, anything other than F is going to go to the error states. For S1, anything other than E is actually going to the error states. Similarly, for S1, anything other than E and I is going to go to error state, right? Are we okay with this? That's something we assume. So it's still a DFA. It's just that for simplicity, we don't draw those errors. That'll be too much. Okay? But in the test, you might get something closer to this or closer to that, in which case you will see the complete diagram. All right? But for this one here, it's a very good question. Just remember, it's still a DFA, but there's an implicit dead state here. All right? And of course, initially the error states is also in the same partition as all the others because it's not accepting. And also for the error states, that one there, you can think about anything in the sigma is also going to go back to the error state, right? Okay, just to make sure. Now, let's run the first iteration. For every iteration, we have to go over each partition. This partition here and this partition here. Just go to one of them. Let's say we go to this partition. And for that particular partition, we have to see if it is possible to find a proper subset, meaning that we cannot find the entire set. If we find the entire set, there's no point to do split. You split a set completely by itself. You're not really doing any splitting. Okay, but anyway, find a proper subset. And the proper subset should really follow the following criteria. We need to find a single character that's in the alphabet, such that, let's say, for example, if we find this particular set of state to be the partition, let's say, in that way, that particular character should really lead them to the same partition, whereas others lead to others partition. They're different. So that's why we can split it out. Okay, I'll just do the first one together with you, just to check. Let's say now we are focusing on this particular partition. And then we're going to try out different characters, and we'll get a feel. All right, let's try. The first character we can try would be, let's say, F. All right? According to this, let's say S0. Let's try follow the number. From S0, and if I take F, which partition am I going to? Pink. Agree? In S0, if I follow F, I'm going to S1, which is in the pink partition, the same partition. Agree? Okay? The same. Over here. And over here, if I try S1, if I do F, what about that? Is it going to the same partition? S1, if I go for F, where would I go? Error states, which is still in the same partition, right? Which would still be in the pink. Are we okay so far? Okay, so now let me just try to write a little bit more neatly. Okay, given that you have got so far, can I say from all the states, S0, S1, S2, SE, and S4? S4 and SE, right? All the states, either one of them. If I try to take F, I'm still in the same partition. Can everybody agree on this? If there's any confusion up to this point, you should ask. That's a critical operation we're doing. All right, so that one is guaranteed we're still in the same partition. All right, so this is not a character to use to justify the split. So we got to try another character. Okay, let's try one more character. Okay, what about the character I? For this one here, if we take character I, it's going to SE, the same partition. For this one here, if we take character I, it's actually going to this one here, which will still be the same partition. If we are now here, character I is going to SE, the same partition. So character I does not seem to be the character to split. All right? Guys, getting a little bit better? Okay. Now, can anybody identify some character which will allow us to see two sets of states? One set got all the states leading to some other partition rather than pink. The other one somehow will stay in the same partition. Any character. I agree? Yes? Let's try. Let's try the E here. If I try the E here, and apparently you can see for this one, S2 and S4, they will lead to the green partition. Whereas for these three states over here, they will simply lead to the states still in the pink. All right? Let's now write it down. So if I got S2, S4, and then I take the E, it's going to lead to the green. And then if I got SE, S0, S1, and if I take the same transition, it's actually going to stay in the same partition. And what I'm illustrating here, just to show to you what's later when you study the algorithm, is really about this condition over here. Remember I said all the states in the partition lead to the same partition. In this case, the green. And the green partition is not the same as the pink, basically. All right? That's something so abstract when you first saw the algorithm. But now we see a little more concrete. All right, so the character E here justify there should be a split. And let's now use orange to create a split for S2 and S4. So now how do we do it? All right, so now I'm going to take this original diagram over here and show you how it should become. All right, we're going to split S2 and S4 out. They should belong to a new partition. And we are not being very ambitious for each iteration. For every iteration, find one split for one character. If you can see multiple split, do it in different iterations. Okay? Are we okay so far about the 3 partitions we have? We'll go from 2 to 3. All right? Now, let's now go further. Okay? Let's say for the second iteration, we're going to try well, by the way, for every iteration, you definitely should try all the partition. In case you try all the partition, but you just cannot do any split, then you're done. You reach the fixed point. You just cannot do any further optimization. All right? Should we split S3 and S5? Should we or should we not? That's an important question. Okay, anybody tell me why or why not? Should we do any split? To justify that, you have to try all the characters in the alphabet. If there's any character there that will allow one of the 2 states going to another partition, the other state will stay in the same partition. That means we need a split. Otherwise, no split. In this case, should we split S3 from S5? William, you said no. Why? Mm-hmm.
Either way, if it's an E, you're going green, and it doesn't really matter.
Yeah, getting there, but sorry, let me just put the SE back, right? We cannot forget about SE,
Yeah.
okay? Okay, SE should be here, and just don't forget, we still have that. I just forgot about that. Okay, in this case, we don't really split because implicitly, any alphabet character from S3 is going to the error states. Also, any character from the alphabet from S5 is also going to here. They go to the same partition. If they go to the same partition, we consider these 2 states as equivalents, so we don't need to split them. Make sense, guys? Okay. So in this case, I can just do a little bit of drawing here. You can think about this one here, and also this one here. Any character. So they go to the same. So we don't split them. How about S2 and S4? Do we have to split them? Well, put it this way. Let's try to argue. If it was the character E, in that way, S2, S4, they go to the same partition. So they will be considered as equivalent. What about any other character other than E? They will simply just go to the error states, in which case they are also considered as equivalent because they go to the same partition. So no split either. All right? So far we tried 2 partitions, the green and the orange, and there's no split. So now we should go to this particular partition over here. And we want to see whether or not we should do a split. And can anybody suggest if there should be any split for this partition? If so, how should we split? I think the color somehow helps because you can kind of see, where the transition will go. William, you want to try?
I guess, well, I know, for example, that if we're looking at S0.
S0 may not be so promising. I tell you why. Because S0, let's try. Yeah, S0. If you take let's say F, you still go to pink. If you take anything other than F, you go to the error states. Right? You kind of stay in the same partition. And for error states, similarly, because any transition you might take in the error state, they will just go back to the same error states. So these two may not be good. What about S1? Looks promising, right? Yeah. So here, why don't we try S1, right? And you can try either E or I. Doesn't matter, right? So why don't we do that? So what we'll do here is we're going to say, let's say E. Okay, so try the character E. And then, in this case, if you try to go from S1, it's actually going to transit to the orange partition. Whereas, for the other states in the same partition, which will be, let me write it down, S0 and SE. In the case of S0, if I take E, sorry, just a little bit loose on my tip. S0 over here, if I take E, it's going to error states. In SE, if I take E, also go to the same error states, which is the same partition. Right? So those two can be staying in the same partition. So that means we should really split S1 out. Let me create another color here. Why don't we do blue? All right, let's now split it further. Okay, so let me just try to copy this diagram here and put it here. And then this one here, basically, so this will be SE, right? And we just split S1 out. That one there, let me put blue here. So far we got 1, 2, 3, 4 partitions. These two we already tried. No split, right? Should we even bother to try this? Can you split a state from itself? Not really, right? So that's why whenever you see a partition with only one state, you don't bother. So the only possible split that's left is this partition. Okay? Now, should we split it? Again, to judge whether you should split it or not, you want to find a single character such that one state taking that single character transition is going to some partition. The other one is going to take you to another partition. They're different. You only split when the two states are unequivalent in terms of the partition they can go to. Okay, anyone suggest whether or not we should do split on the pink? Should we or should we not? Split with F? Yeah. Exactly. You can see S0 taking F goes to blue. SE taking F still stay in the pink. They're different. Exactly. All right, guys? I know you're still learning this, but that's okay. This one is kind of confusing, but hopefully this example kind of helps. We'll do one more example together. So the way to justify this is we can take F, and then in this case, we can say S0 taking F will lead you to the blue one over here. And for SE, if you take the same character over here, it's going to remain in the same partition. All right? So let's create a final one, which will be, let's put S0. Let's say purple. All right? And of course, in the actual quiz, you wouldn't be able to, you don't want to bring that many highlighters to actually draw. So I'll show to you how you can do it textually, just in a moment, right? But for now, let's stay with the color, just for now. Of course, if you want to bring that many highlighter, I wouldn't mind. Okay, that might be the final one. And then let me finish everything, and then I will suggest how you should write your answer in the test. All right? So we're going to split S0 out. That one there is going to be purple. All right? And do we have to bother with any further split? We don't need to, because this one we already tried. This one we already tried. All these three partitions only got one state in the middle, in the set, so we don't need to bother. Then we are done. 1, 2, 3, 4, 5. 5 partitions versus 1, 2, 3, 4, 5, 6, 7. So we go from 7 states into 5 partitions. Each partition will represent a state in the final DFA, which we're going to draw. Let's now try to make a conclusion. For the first one, we're going to do very completely, right? Just to make sure everybody's is okay. Okay, let me just open a new page. This is what we begin with. All right? This is what we ended up with. Okay, let me make a notes. So in the beginning, input, we got 7 states. The output, we got 5 partitions. And how do we draw the corresponding DFA? That's also important. That one will be very similar to how we did it for the subset construction. Very similar. Let's try. All right? Let me write down all the partition first. We got S0 by itself, which will be a states. Also, SE, S1. SE, it by itself. Also, we got S1 here. Also by itself, like a subset state, basically. S2, S4. S2, S4 as a single states. S3, S5 as a single states. Okay. Let's now first of all work out which one should be the start state and which one should be the accepting states. All right. This one here, S0 used to be the start states, right? Used to be. S0 will still be the start state. That one's easy. What about accepting states? As long as the set contains either S3 or S5, they should be accepting. All right. Which means it's going to be just 1. Okay, that's accepting. And how do we draw transition? Well, just follow that. For example, let's say over here, if we go from S0 taking F is going to S1. S0 taking F is going to S1. So that one's easy. S would be F. S1 go to S2 by just E. S2 go to S3 by E. And also S1 go to S4 by I. And also S4 to S5, S4 to S5 by E. Oh, that one's done already. You don't need to repeat. All right? And then what about everything else? They will go to error states implicitly. And that's the DFA. And are you convinced this is actually still the same? Well, we said it used to be either FEE or FIE. Indeed, FEE or FIE. And you can do the percentage calculation, drop from 7 states to 5 states. I think that's pretty good. Okay? Almost 30% drop. Any question about this? Okay. Are you sure? All right. So I think for the algorithm here, I will leave you guys to maybe go back and maybe take a look at the algorithm once more. So now things will make more sense. So now you can do it. And I would suggest before I let you go for this topic here, why don't we do one more? Why don't you guys think about whether it should be any split? Maybe, maybe not. And here we are assuming the following. Sigma is A, B, and C. And this one here, we don't have that implicit dead states, so we are fine. Actually, we do. We still have it. Sorry about that. The last one we don't have, the dead state. So don't forget about SE. Okay, so I'll help you in the beginning. It's going to be between accepting states, which will be D1 over here, D2 over here, and D3 over here. Non-accepting states will be D0 and also SE. That's the initial. You guys' job is to tell me whether or not you think we can somehow split either the green or the pink. If you don't think so, you can also justify why not, right? Okay, take some time to think about it. I would say at least for the pink partition, it should be quite obvious, right? Whether or not there should be a split. We have seen that already. That one should be quite obvious. Why don't we start with the pink? And then for the green, I can let you think a little bit more. How about let's do the pink? Should we split D0 from SE? Should we or should we not? We should, right? William, what character should we use to justify? Absolutely, yeah. It's obvious, but we should write it down, all right? So here, if we say we take A, right? For D0 taking A, it's going to the green partition, in which case I would suggest you simply say it's going to the partition of D1, D2, D3. Whereas for SE, by taking A, where should it go? The same, right? The same states. In which case, it's going to be the partition containing D0 and D1. Right? You can think about this notation I'm suggesting rather than color. You can do either way in a quiz or exam. I don't mind. Okay? I'll prefer the color, actually, if you bring the highlighter, but it's not required. You can think about this one here is a partition. Okay? All right? All right, that's a justification. They are different partitions, so we're going to split it out. So what I would do is I'm going to do that. So this one here, let me just say, how about orange? Okay, so I'm going to put it here. Let me copy that, and then put it here. Okay. Oh, by the way, sorry, before I forgot. In the previous example there, it's better to number them. Step number 1, number 2, number 3, number 4, okay, just in case. This one here, this will be number 1, this will be number 2, all right? And we're going to split the 0 out. It's going to be orange, which is awesome, all right? Okay, we don't have to worry about D0 and SE partition anymore, only one state. Yes? Sorry, say it again. Oh, D1? D1 is actually accepting states. Oh, you mean this one here or this one here? SE over here? D0 SE. Oh, thank you. Thank you. You know, sometimes I don't really mean what I wrote. I absolutely meant SE. Thank you. You guys are good. Now, should we split green? This one is a little bit tricky. I was doing this exercise earlier this morning myself. It took me a little bit longer to figure out. I wouldn't say how long. Please.
I don't think so, because regardless of what state you're in, whether you choose B or C, they're all going to end up in the same state. So like D1, if you pick B, you'll end up in D2. D2, if you pick B, you end up in D2, D3.
Okay. Do people agree? Why don't we do some exhaustive check just to convince ourselves? All right. Let's try A first. If we do A, D2 taking A is actually going to here. D1 taking A is going to over here. D3 taking A is going to here. So the same partition. So A is not good. All right, let's document it. If we do A, D1, D2, and D3, all of them taking A will just go to the partition with SE. What about B? D1 taking B, go to the green. D2 taking B, also go to the green. D3 taking B, also go to the green, right? So B is good. Let me write it down. So either D1 or D2 or D3, if you take take B, you just go back to the same partition with D1, D2, and D3. Finally, why don't we try C? D1 taking C here. D2 taking C here. D3 taking C over here. The same partition. Yeah, so you're actually right. Okay, good. So that's how you justify, right? D1, D2, D3. And then C, D1, D2, and D3. So that will be the final partition. In which case, what we got is, how many partitions we got? 1, 2, and 3. Only 3 partitions, so only 3 states. We have reduced from 1, 2, 3, 4, 5 into 1, 2, 3. All right, let me write it down, and then how to draw the corresponding DFA, I'll leave that to you. All right. So we go from 1, 2, 3, 5 states down to 3 partitions. Exercise will be to draw the DFA. All right. And there is one more over here, exercise for you. And then I'll post a solution during the reading week, so you guys can compare. All right, try to do that, and then compare your answer. All right? Exercise. Yeah, for those of you who might be interested, feel free to extend your assignment number 1 to do this minimization. Feel free if you're interested. Now that you already got a programming infrastructure over there. So it should be quite easy to add just another method to apply, right, if you want to. But it's not required. All right, that's about it. What I want to talk about minimizing DFA. Any question before I move on to the next one? Everybody's okay, right? So if I give you something like this, you should be able to do it in a quiz, right? Or the exam. Okay, everybody's happy. That's good. Awesome. Good. All right, that's now final topic for the scanner. And then we can move on to a little bit of syntactical analysis today. Okay, so this will be some like a single exercise which will synthesize everything we have said so far. Let's say given this particular regular expression, okay, you want to derive the equivalent DFA with the minimum number of states. Let's say you're given this question. How many conversions would you have to do? This is the input, regular expression. This will be the output, the DFA with the minimum number of states. How many algorithms or how many procedures do you have to apply? We can just enumerate them. Henry? Yeah, so regular expression to epsilon NFA to DFA, and DFA minimized, 3. Right? Regular expression.
I'm thinking of something else.
Sure. Regular expression to epsilon NFA, number 1. Number 2, epsilon NFA into DFA, and then number 3, DFA, minimize it. That'd be 3. All right, guys, I'll leave that to you. That's just another exercise to put everything together. All right? And final thing to talk about very briefly. Okay? How do we well, DFA is just one single component for the scanner, but it's definitely the critical components. Let's see how we're supposed to implement the scanner. Basically, now we have to worry about syntactic categories. For example, one category could be just keyword. One category could be identifiers. Another category could be just white spaces, right? Each one of them is going to have their own pattern specification as a regular expression, right? So you can think about overall, the scanner is actually going to be more like category number 1, regular expression. Category number 2, regular expression. Category N, regular expression. By the way, this one maybe should be R2, not R1. All right, I'll fix that. Minor typo. Right? So the scanner itself is going to compose of, it's going to consist of many regular expression. Okay, but we're going to go over some algorithm just so that you got some idea. And of course, for each regular expression, you can think about it should be somehow converted into the minimized DFA somehow, right? Following what we just said. Okay, so what I'm going to do is I'm going to show you very quickly some algorithm. Okay, so this one here. Okay, let's do some example. Let's say we got this regular expression. Okay, but this one is not exactly what we said in the class. I just took it from the textbook. So this one to say we got some single character R, and then followed by a single digits, either 0 or 1 or 2, all the way to 9. As many as you like, at least 1. That's actually how we specify the name of some register. R21, R123, or R5, etc. All right. And that'll be the DFA, right? So this will be the minimized DFA that we can assume. We already got it. And then there will be some extra level of complication of how things work. I'll introduce that over here for the example, and then I'll show you the algorithm quickly, and then we'll trace it. And that's it. Okay. We're going to have some classifier, and a classifier simply means whenever you see some character, you want to know which class it belongs to. For example, if we see the character R, that means we want to do some register, just R. If we see any numerical digits, it's simply digit. If we see the end of file, it's simply considered other category. Similarly, if you see anything other than what we have mentioned, it will just be other. Okay, it's not really worth it to further categorize them. Right? We only got 3 categories. Number 1. And then this will be the transition table. All right, that's something we are pretty familiar with. That one we can just deal with it when we trace it. Number 3 would be what kind of token should we actually return? All right, this is to say, if somehow the final state you decide to terminate your program happen to be S2, that means the token you're going to return will be register type. If the final state you actually terminate the algorithm, once you finish reading the input, happens to be, let's say, S1 or S0 or error state, it will just be invalid token. In which case, you will see some red underline, for example, in Eclipse. Right? The scanner will report some error. So these are the 3 tables that will be necessary for us to make the algorithm work. Okay? And this is the algorithm over here. Do you need to memorize it? Absolutely not. If I ever ask you a question about the algorithm, I will include it in some appendix. So you can definitely have reference to it. Don't memorize it. Maybe just have some idea to know what should be done. So I would suggest I'll trace maybe at least 1 input together with you, and then you definitely get a feel about how it should be done. Okay, let's do it quickly. This will be kind of this process we have to go through, especially when we talk about parsing algorithm after the reading week. So let's now do that just for the scanner. Okay, I put everything that should be here, that should be considered. Token type, token type, transition, and here, right? Or category, and also the return type. Let's say we want to process this input with only 3 characters, R, 2, 4. Eventually, that would be considered as a valid token of type register, eventually. Register here, eventually. Okay? Whereas, if I give you just another input, let's say over here, in this case, you can see there's no space in between. So this should be considered as a single hole. In that way, this would not be considered as a valid token, for example, as far as the tables here are concerned. All right? This one will be left as an exercise for you. But let's do this one here together. All right? Let's trace it. We'll just use a stack. Okay? And let's now try. Okay? I'll try to do it as quickly but clearly as possible, and then we can move on to parsing. Okay? Let's try. First of all, the initial state will be S0. I'm going to put it here, S0. And then the word we have processed so far will just be empty, epsilon. And then we have some empty stack, which is over here. And then we try to push the word bad. Well, of course, this is only pseudocode. How you actually push the bad into your Java stack is kind of up to you, right? Just conceptually. So I'm going to put the bad symbol over here. The bad seems to be a very old school style for you to know whether the stack is currently empty for some reason. But anyway, I'll just follow what's mainly, I kind of adapted a little bit from the textbook, but let's just keep that. All right, that's the initialization. And let's look at this condition here. We say that as long as the state is not equal to the error states, we're going to continue. All right, this while loop, the first while loop. Let's try. The next character over here is going to be R, right? So the word is now going to become just R. You know what? Let me just try to do a little bit better. For the first iteration, let's use green. In this case, it's going to be R, so the word is going to be R. And then, what about the states? The current state is S0. Is S0 an accepting states? Not really. Just to remind yourself, if you look at the DFA over here, the only accepting states, let me just remind you about the diagram here, is S2. Okay, just remember that. Let me make a note here. S2 will be the accepting states. Okay, just remember that. Okay. So initially, S0 is not really accepting states. It is not. So we don't have to reset the stack. And we're going to push the states into the stack, which will be S0. All right, and then what about the category? We're going to look up the table. Okay, so go to the category table, which is over here. Given the index, which is the character, which is R. According to it, R is the category of register. All right, so that's why we're going to put the category as register. Okay, so far so good. And then what about the states? How do we make a transition? Go to the delta over here, which is over here. Oh, sorry, not here, over here. And then where is the states? The state is S0. S0 over here. And then the category, as we work out, is register. The target state should be S1. So that means now the state will be updated from S0 to S1. Everybody's okay, right? All right. And then if you try just another iteration, okay, and to make things a bit easy, why don't I decide just R2, not R24, just easier, okay? The next character to process will be, because the current state has been updated to S1, is S1 an accepting state? It is not, so we are not terminating yet. We're not exiting just yet. So we're going to read the next character, which will be just 2. And then the word is now going to become R2, being expanded. And then the states right now is actually S1. Is S1 an accepting state? It is not, so we don't reset the stack. All right? And then we're going to push the states onto the stack, which will be S1. And what about category? Help me out. What should be the category now? How do we look it up? Go to the table here, and then the character we are considering now is 2. Right? Digit. That's the category. All right? So that means the category is now changed to digit. And then for the states, we are now in S1. And then take a digit, we go to S2. Promising, because S2 is in accepting states. Right? State will now be changed to S2. It's a very tedious, but at least you know how the algorithm works. After this, because now the state is indeed an accepting state, somehow we can just exit from the loop. And then you will see that we don't have to roll back. So eventually, what you will see is we get a return just R2 over here being the register token, because we're now in S2. Right? Because after the transition, state will become just S2. Right? So that's about a successful case. What you want to try is, what if I got something like this? Some valid token in the middle. At some point, we're going to transit to some error states at some point. What's going to happen afterwards? I'll let you find out in the algorithm. All right? Guys, any question about this? We okay? If you got any question now, it's not time to ask. If you want to dive deeper. Otherwise, I would assume you're going to dive deeper into the algorithm. At least for the invalid case, I just suggest in the next slide. Right? So we got another 20 minutes to cover new lecture. All right, I presume everybody is okay. This kind of a tracing will be very important, especially once we get to the parsing later after the reading week. So just get used to it. Right? I'll try to trace as much as I can in the lecture together with you. Other than that, you will have to do it too. All right, I'll put it here. Exercise. All right. If no further question, that will be it for the scanner, the lexical analysis. So we're done. We can now move on to this one here. If no more question, I would suggest we take a 2-minute break, and then we'll start this new lecture. All right? Take a break. Okay, we'll take 1 more minute, and then we should get started. All right, let's now resume. Okay. Sorry, just one more little detail I want to mention just about the tracing we did very quickly, just in case you want to revisit this example. Actually, I think you should. Okay. You can assume that for this particular input over here, there is an end of file, EOF, right? For those of you who took 2031, you know what EOF really means. That means the end of the input. Okay. So one thing to note. Once we get to the accepting states over here, S2, and when we reach the end of the input and we got EOF, that will make a transition to SE, from S2 to SE. So once you get to the SE, that is how you exit from the while loop, which I didn't say before the break, right? Just to mention that. All right, just remember. Of course, when you do that exercise there, just remember there's also EOF here. All right. Okay. All right, let's now talk some light stuff about parser. The heavy stuff will come after the reading week. So we're gonna interleave a little bit between parser and also design patterns. So you will actually be beneficial for your projects. Okay. Let's now talk about syntactic analysis. Okay. Okay. So what we have done is, if you recall this diagram over here, okay, it's a bit small, but let me read it. We have done the lexical analysis for the scanner, and the scanner is going to return a sequence of tokens, not sequence of characters. Once we get a sequence of tokens, we are going to see whether or not they will make syntactical sense as far as the parser is concerned. Of course, we've got to consider some context-free grammar, which we'll talk about. After that, we're going to return some parse tree. From there, we're going to do further semantic analysis. And you will see some semantic analysis, some easy one, when you see the Untitled 4 tutorial video. All right? But now we're going to focus on how we build a parse tree. And as you look ahead, there will be two major algorithms we have to learn for this course for parsing. Number one is called top-down. The other one is called bottom-up. Kind of similar to when you build a heap. You can either do top-down or bottom-up. Similar idea. Okay? But we'll get there one by one. And it's going to be a sequence of classify, right? You can see classify, right? Depends on which category each token belongs to. Okay? And we're going to parse the token into abstract syntax tree or parse tree. And then upon termination, we're going to, again, if there's any error about a sequence not being able to be parsed into a tree, we're going to report it. Otherwise, we return the tree. Okay? In the case of the Untitled 4, you will see you just have to work on recursive tree structure a lot. Okay, that's something you will see. All right, and let's now do a little bit quick review on the context-free languages and also grammar. That's something you might need just to brush up your mind, because you will see them also in the Untitled 4. Okay. So what we have seen in the lexical analysis, they correspond to regular languages. You can use a DFA, NFA, or regular expression to specify them. And by the way, guys, have you encountered this term before, pumping lemma? Don't worry, we're not going to cover that. Don't worry, I just want to mention that, right? I didn't even mention in the previous lecture. For those of you who, for example, you're interested, feel free to talk to me. I'm quite passionate about this kind of stuff, actually. If you want to say, well, just very briefly, if you actually want to prove that a language is not regular, you will need to prove by contradiction. Similarly, when you actually want to prove a language is not context-free, meaning that you cannot really have a grammar for that, you also need a pumping lemma. There are two versions of pumping lemma, one for regular language, the other one for context-free language. And the pumping lemma for context-free languages is really a lot of fun. But don't worry, we're not going to cover that in this course. It belongs to 2001. I'm not going to trouble you. Okay. Anyway, that's the only place I'll mention about pumping lemma. That's the only place, only for your information. But if you're curious about having further discussion, I'll be happy to engage. Right, so basically, anytime if you think the language you have has some recursive structure, most likely they're context-free. They are not regular. Okay? For example, this one here is a very typical one. I'm pretty sure you have seen that before. This one here saying that we got equal numbers of zeros and ones. But the problem is n can be infinite. So that's why DFA cannot handle that. DFA got some limited or finite amount of memory or number of states. So that's why it cannot be specified by some DFA. Okay, context-free grammar. Anything that can be described using a recursive fashion, you can use context-free grammar. We'll give you some example to brush up. Any language that can be represented by context-free grammar, meaning that once you get a grammar, you will be able to derive an infinite number of strings from the grammar. And those strings represent the context-free language. Okay, good. Let's now see some example over here. I will let you guys just do one exercise, but not this one here. This one's simple. I'll let you do a little more challenging one. Okay. Let's say the following language is non-regular, right? Similar, we just have a hash sign in the middle. Okay, and I will show you the grammar directly. Okay, and let's now go over very quickly about the terminology, I think you will hear those terms as well when you study the tutorial. Okay? Do you guys remember, for example, for things like here, right? A and B, also for 0, 1, let me use a different color. That means they belong to different category. For 0, 1, and also hash sign. Do you remember what they are called? Which one is terminal? Yes, I agree. Terminals. Oh yeah, that's good for sure. Terminals. Yeah, just give me one moment. Let me just finish that. I'll definitely take your question. You can say non-terminals or variables. Either way. Yes, please.
N can be equal to 0 or greater than 0. Do we actually need A going to B, or can we just have A going to 0, A1, or A going to 9? Do we need that B?
Let me see. In this case, that would be just 0 and 1 and. That means without. Let me see. Yeah, I think A should also be able to be epsilon. It seems like, right? Yeah. Okay, I agree. That's pretty good. For the sake of illustration, why don't we say? Why don't we say that? Okay, I'm going to change that. But you know, precision is really important. I agree. Okay, guys, do you see why I'm changing this? Because currently in the grammar here, it's not possible just to have 0, 1, right? Because whenever you want to replace the A here by B, you must replace it by a hash sign. It cannot be epsilon. That's why. That's why I'm changing this to larger than. Okay? Let me change that just for now. All right? I'll fix the typo as well. My bad. Okay. And one more terminology to say, or two more actually. There is a special variable here. The first one is called a start variable. By the way, every term I'm talking about right now, you will see what I mentioned in the Untitled 4 tutorial. So I think this will be nice. Start variable simply means if you want to derive a string from the grammar, this will be the start symbol to start the derivation. We'll do some example. Okay? And then, one more thing to say. If I have some variable at the left, also some, oh, you know what? How about this? This one is okay. This one is to say we got some variable, either start or not, and then we got some terminal, non-terminal, like a mix. It is called a production rule, which is also very important. You want to specify different alternative for the patterns. Production rule. All right. Yep. Any confusion, anything you need clarification? I hope that's okay, right? And just for you guys, just to motivate you. When I first actually write into compiler technology, it really confused me a lot in the following sense. Here, you can see I got 3 production rules, right? When you get to Untitled 4, a tool like Untitled 4, what we're going to do is, after each production rule, you're going to see a block of code in Java. And the code you specify over there is going to specify how you're going to build up the parse tree. That's something you will struggle a bit when you study the tutorial. I would say that might be the most confusing bit when you're learning about a parser generator like an Untitled 4. Let me say that one more time, just remember that's something you will write into. Production rule, you will see the exact correspondence in Untitled 4. But after every production rule, you will be able to add usually curly brackets. Inside there, you can add as arbitrary Java code as you like to say how you would like to build the parse tree once the parsing is done. This is where the magic actually happens. So when you actually study the tutorial, pay attention to it. All right? So this part is theory. Once you see that, it's practice, how we build a compiler. All right. All right, let's see. Yeah, so this part here is just about how you can write, how you can derive different string. Why don't we just do example directly? I'll let you read the slides. I don't need to read it off to you. Okay. let's say, for example, this one here, what will be the shortest derivation? It's quite obvious. The shortest derivation, like a string, would be just a hash sign, right? How do we do that? Basically, by the way, this would be a hash sign. So you would say A, right? You can derive A into, according to this. Let me say production rule 1, 2, and 3. By 1, oh, actually by 3. Beg your pardon. In this case, it would be just 2. Into B, and then B by production rule number 3, it would just be hash sign. Whenever you got into a string containing no non-terminals, that means everything is already determined, and you're done. That's a one string, all right? So this is a derivation result. And you can also visualize the derivation using a parse tree. In this case, it looks like this. A derived into B, derived into hash sign. It's a tree, right? Like a slanted tree, right? Just one way. Okay. And easy question for you: can you have a parse tree for this, and can you have a parse tree for that? Let me call this A. Let me call this B. Can you have a parse tree for A? Can you? Can you not? Why don't we try? For A, we can do A by production rule 1. We're going to have 0, A, and 1. And then 0 and 1, we cannot do any further derivation. What about A? We got another 0. Well, we just got basically 0 and 1 here. We need another pair of 0 and 1. So again, by 1, 0, A, and also 1. Right, we got 0, 1 here. We just need one more. By the same derivation rule 1, we got 0, A, and 1. And then by derivation rule 2, get to B. And then by derivation rule 3, we get to hash. And if you look at the leaves, 0, 0, 0, hash, 1, 1, 1. So we do have a derivation, right? I'm just doing some simple example so you know what to expect, all right? And can you guys just tell me, do you have a derivation or parse tree for this? No? People agree? If you don't agree, you just need to show a parse tree to me. It turns out you cannot, okay? No. However, exercise, modify or extend the grammar to allow it. All right, that's you. Maybe just one single production rule might just be sufficient. All right, I'll let you guys try that. All right. I believe I got one more. And then I want to leave just 1 minute or so just to talk about what you should do also for the project. Okay. All right. It's a very big lecture. As you can see, I got about 90 or so slides. So we got lots to talk about. So today, and also possibly in the first week, we're just going to review some simple grammar. But after that, we're going to talk about parsing algorithm. All right? Parse tree. And then this one's easy, just about palindrome. Okay, you can study this one here. And this one is about you having a word and followed by its reverse. That one is also very straightforward. Okay, I'll give the solution to you. You can study that. And this one here is interesting. Okay. Okay. Now, we want to have a context-free grammar over here for the set of binary strings. Each block of zeros followed by at least as many ones as possible. Okay. And now you can see, for example, you got 3 zeros. So that should be followed at least 3 ones. You got 3 zeros followed by at least 3. So it can be 4, can be 5, and can be 6, and etc. Okay? I would suggest the following. you can copy down this problem description here and try yourself to come up with the grammar for that. And then I will post the slide maybe tomorrow. You can compare your answer, okay? Rather than just looking at the grammar directly. I think it's very likely the answer you come up with is quite different from that one, which is okay. You can always come to me. I can maybe judge together with you whether that's actually also correct. All right, that's the exercise I would suggest you do. All right, so now I think we're good up to here. And then after the reading week, we'll just continue to talk about parsing. I'll interleave it with design patterns. And one more thing to say, just give me 1 minute. Okay. For your project, I think it now might be a good time for you to look for your buddies in the project. I think most likely I'm going to require at least 3 members in each team. So we need 3 or 4 in the team. Okay, so you can maybe start reaching out to your classmates, approach them. And for those of you who think you might need some help on forming a team, feel free to email me. And then at the end, if I got different people there, I can try to see if I can group you guys. But I think you guys should just find your own team. 3 or 4. All right, thank you so much. And don't forget 2 p.m. tomorrow to submit your assignment. And then I'll see you after the reading week.